some pills that are in the market, and we want to see whether these are the high risk or the low risk. Then we plotted that distribution on this scale of low risk and high risk. Then if the data is more skewed toward right, which means there are more data points that are showing the high risk phenomena or high risk distribution, because if we are going towards right, there are higher values than the mean. The mean is over here. See, the mean is here, and the tail is skewed towards the right. So there are more points that are higher than the mean. And then we call this as a positively skewed. We call this that the data set is positively skewed. The tail is more towards right, or the tail is more towards the higher data point. So the curve B is called positively skewed curve. Curve C here, see, if you see this, it's more skewed towards the left, which means the mean is here in the center, and the tail is skewed or is extended towards the lower values, towards the low data points, or towards the low risk. We call this shape or this type of skewness as the negative skewness. So when we plot our data set, we can see type A distribution, or we can see type B distribution, or we can see type C distribution. Maybe I didn't mention this, but please keep in mind that normal distribution is always for the continuous data. So the values are always continuous. In fraction, it could be whole, it could be fraction, but it's always continuous data set. Normal distribution is plotted for the continuous data set. So either you will see, when you plot your data, either you will see shape A, or you will see shape B, or you will see shape C. So shape A is the perfect, symmetrical, normally distributed data set. In this case, in a perfect normal distribution, the mean, mode, and median are all same. They have the same value, and they lie right in the middle, right in the center of the data set or of the distribution. In type B, which is the skewed towards right or skewed right distribution, or the positively skewed distribution, the tail is skewed towards the right, or there are higher values which are dragging the tail towards the right, away from the median, or away from the mode, and or the higher the data points with higher values than the mean. And then if the data set or the distribution is skewed toward the left, then it's called negative skewness, or negatively skewed data, or skewed left distribution. So which means there are more data points which are skewing the data set or skewing the distribution or dragging the distribution towards the left of the mean, and the mean is always here at the peak of the data is. How do we compute the skewness? The skewness is computed 3 times mean minus median over standard deviation. This is the equation that we use to compute the skewness. And again, it just gives me an idea how skewed my data set is. It's telling me that, see, my data set is not highly normal, or not, sorry, it's not highly normal, it's not normal. It's highly deviating from the normal, whether towards the right or whether towards the left. So the shape of the distribution is giving me an idea about the distribution in my data set. And then the other thing is related with the shape of the distribution is that how flat or peaked our distribution is, and that is known by this term which is called kurtosis. So when we want to know about the shape of the distribution, remember there are 2 parameters: skewness, whether the data is left skewed or right skewed, or it's symmetrical, and the other parameter is kurtosis. The kurtosis tells me what is the peakedness or the flatness of my data. See, this green curve is a normal distribution. This represents a data set which is symmetrically or normally distributed. It has certain peak to it. However, if the peak is higher, like than this green curve, or the peak is lower, or this central is lower than this green, and there's a more spread, horizontal spread into this. So this also tells me about the shape of the distribution. Red refers to the peakedness, because we say that it's more peaked towards the mean, towards the center. Yes. Here, negative value, no. Here, negative value does not mean that it's skewed towards the left. It means that it's the flat. The top is a flat. The top of this data set is flat. It's more. There is more spread in it. See this in this blue curve. There is more spread into it, and it's flat. There is no such peak into it. Negative in terms of kurtosis, it's not telling me whether it's left skewed or right skewed, but it's telling me about this, the flatness of the data. Okay? Yes? No? Okay. So this is a flat. The top of this data set is flat, and it's more spread out. Over here, it's more peaked, and of course, as the name suggests, there's a high peak in this data set. And the kurtosis, and the kurtosis of a perfectly normal distributed curve is 3. So we measure anything in terms of whether it's +3 or -3. Like we always subtract 3, where 3 is the kurtosis of the normally distributed data set. This is the equation that we use to compute the kurtosis. So x minus x prime, x is the any data point 1, 2, 3, 4, 5, 6, and all the data points that we have in our data set. Xi minus x prime is the mean, divided by the standard deviation, whole divided by the total number of data points that we have in our data set minus 3, and 3 here. The reason we are using 3 here, because the normally distributed data points or the data set has the kurtosis of 3. So again, when I plot the distribution, when I find out so let's do a little recap. We found out we calculated the basic parameters of our data set, which is mean, median, and mode. That gave me some idea about what is the underlying basic statistics of the data set that I calculated, whether it's related to the heights of the students in the class, whether it's related to the inches of the rainfall. Just to get a sense out of it, I say this is the mean, this is the major mode, and this is the median. Now again, when we are talking about the dispersion in the data set, see, if the data set is highly dispersed, if there is too much variation, if the standard deviation is high, then the mean of the data set is not very stable value, or I am not 100% or 95% or 90% confident about that mean, because one or a couple of values in that data sets were lying at the very high end, and some of the values were lying on the other hand. So if the dispersion or the standard deviation is too high, then the representation, these basic parameters, or the conclusion that I'm drawing out of these all these data sets, or by computing these parameters, are not very strong. The decisions that I'm making based on such data set is not very strong. I have doubts. Maybe I need to collect more data set. Maybe I need to see there was some failure in my experiment. I should find out the reason. Okay, so we find out the central tendency, mean, median, mode. We find out the variance in the data set. We find out the standard deviation of the data points from its mean. These numbers give us some idea about our data set, and then we plot the data set. We plot the distribution of the data set to see whether it's normally distributed, or if it's not normally distributed, then the standard deviation gives us some kind of an idea, and when plotting it gives us more, if we are then more authenticated in our claim about the type of data set that we have. So we draw we plot the distribution. By plotting the distribution, the shape of our data set tells us whether it's a symmetrical distribution, whether it skews toward right, whether it skews toward left, and then the shape of the distribution. And remember the shape of the distribution of our height data set that we saw here, and we plotted a normal curve. We had high peakedness over here. So that told us that, and that tells us that our data is not exactly symmetrical towards its mean, and it's not exactly normally distributed. Now, why do I need to plot? Why do I need to know the distributions, the shape of the distribution? Does kurtosis and skewness tells me anything? And do I have to do something about my data set? Yes. If the data is too skewed towards right or left, if there is a high peakedness, or if the data is too flat, which means when I develop the models using this data set, then my claim would not be very strong. I am not 100% sure. We are never 100% sure, so I take it back. I'm not, even when we have our confidence interval, when we have our confidence bounds, we are in the statistics, we say 99% sure or 95% sure, and 95% sure is the most commonly used confidence interval. So our decisions based on those such data sets which are highly skewed, or they have high kurtosis, negative or positive, is not very strong. So we need to do something about that data set. For example, when I collected the data set for my dissertation, due to the variation, maybe it's because it was mostly the data set, the field collected data. I went out in the field, and you know that in the field we cannot control all the parameters. When we do the experiments inside the lab, the environment is highly it's protected environment. We can control the environment. However, when we go outside in the field, when it's real field, there are many factors that we cannot control. So when I plotted the data set, I did the skewness, and I computed the skewness and kurtosis. I found that my data was not exactly normally distributed. Then the models, I did not want to develop the models based on the skewed data, because then my claim would not be, I would not be very confident about my claims or about my conclusion. In that case, then what we do is we do the transformation of our variables. So if it's a linear variable, then I transform it, either I compute the log of the variable, or I compute the exponential of that variable. There are again hundreds and thousands of transformations that we can do. The power transformation, the log transformation, and we do these transformations so that the distribution of our data set is very close to the normal distribution, and then using those transformed variables we develop the models. Okay, is it clear? Did you get something out of it? Now, are you getting a feel out of how your data should, like, what once after collecting and then presenting your data set, then when you come to the real analysis, what are the first steps that you need to take? Okay? Yes? No? Any question? Okay, thank you, Mudassar. Okay, let's take a 5-minute break, and then we'll discuss the more our slides. Okay? Thank you.